Hi everyone, welcome to goclasses. Please let me know. Audio, video, volume, echo, is everything clear? Is everything fine? So we were discussing GateCS AIMT3 solutions, and our previous session it got abruptly ended. It is some issue with YouTube. We have already raised the complaint and I think it has not got resolved. So basically there is some issue I think with Zoom and YouTube integration. I am not sure what is the issue, but now we have started this session with OBS, which is a software. Okay, so with that we have started this session. Okay, so hopefully this will not get interrupted and we will complete our discussion of GateCS AIMT3. Okay, so let's start this discussion now with OBS. Okay, so let's start now. Everything is clear? Audio, video, volume, all clear. Very good. Okay. So we are discussing GATE CS 2026 All India Mock Test 3 AIMT3 detailed solutions. And in the previous session we were discussing a question. Almost discussion for that question we have done. Okay, so let's resume from where we got interrupted. Okay, so I am starting. Let me tell you that all the AIMT solutions you can find in this playlist. To find all the all India mock test solutions, then just on YouTube you put on YouTube you search go classes AIMT. This playlist will come, and here you can find all the parts. You can see this is part 1 of AIMT3. Similarly, all the previous AIMT solution, AIMT1, AIMT2. Okay, so all these you can find in this playlist. Okay, go classes AIMT playlist we have created. In this playlist you will find everything. Okay, so let's start. So this question we were discussing, and almost the complete discussion we have done for this question. So the link I will provide you in the description. You can watch that previous session. In that previous session, basically this question we have solved. Okay, this pipeline based question, this we have solved. And in this question, basically I was discussing about throughput. I was discussing. Okay, so you can see the definition of throughput here. The throughput definition says that the throughput of a k stage pipeline, if you have a k stage ideal pipeline means there is no data hazard, there is no structural hazard, there is no control hazard. You have a ideal pipeline. So you can see the throughput of a k stage ideal pipeline. What is that? That is basically frequency of the clock. This is what we were discussing. And the instruction latency, that is the individual instruction execution time. Okay, so you can see instruction latency. This is basically individual instruction execution time. Individual instruction will go through all the stages. So the in any ideal pipeline, if you have an ideal pipeline without any hazards, then in that case, any individual instruction, how much time it will take, the execution time of an individual instruction, that will be equal to how many stages you have, these many cycles. Okay, because every individual stage will complete its task in one cycle. Okay, for any individual stage, if you see the time taken by that stage, that is basically one cycle. Okay, so you can see individual instruction will go through all the stages, so it will take how many cycles? It will take, if you have 8 stage pipeline, then it will take 8 cycles. If you have k stage pipeline, then it will take k cycles. And you can see we were discussing about throughput. So you can see if you have 8 stage pipeline, ideal pipeline, let's assume. Okay, if nothing is given in the question, then of course we will always assume that we have ideal pipeline. If no information about hazards, dependencies, okay, if that is not given in the question, then we always assume that we have a ideal pipeline. Okay, without any hazards, without any stalls, so we have a perfect pipeline. Then in that case, you can see what is throughput. To calculate the throughput, you assume that you have large number of instructions, and the definition of throughput, that is basically per second how many instructions complete. So you can see that if you have an ideal pipeline, k stage ideal pipeline, then in one cycle one instruction will complete if you have large number of instructions. To calculate the throughput, we always assume that we have large number of instructions. So you can see that in one cycle one instruction will complete. Let's assume that one cycle time, that is 0.5 nanosecond. Okay, so you can see assume assume, you can see cycle time, one clock cycle time. Assume cycle time, that is, let's assume capital T. Okay, you can see, let's assume it is a capital T. So capital T. So you can see, in capital T time, one instruction is completing. So tell me, per second, how many instructions will complete? So you can see, per second how many instructions will complete, that will be 1 divided by T, there these many instructions. Okay, and what is 1 divided by T? You can see this is basically frequency, yes or no? Okay, so you can see per second these many instructions are completing, and overall you can see it is basically frequency. Overall it is basically, throughput is basically frequency if you have an ideal pipeline. Throughput is basically frequency, clock frequency. Okay, I hope you understood this point. So it is a very easy point. Is it clear? Let me know. So this particular question, is it clear? You can see this screenshot. In this screenshot I have put all the information that is required to solve this question. So you can see that instruction latency, that is individual instruction execution time. So if you have k stage pipeline, then instruction latency, that will be k multiplied by clock cycle time. Okay, so you can see k times k multiplied by the period of clock. Okay, and you can see throughput of a k stage pipeline, that is basically frequency of the clock. Okay, and this is the proof. You can see that this throughput of a pipeline, this throughput is basically frequency of the clock. Okay, if you have ideal pipeline, then this is how you can find the instruction latency and you can find the throughput using these definitions and using these formulas. Okay, so we have already seen this. Now let's move on. Let's solve this question. This is another question from computer architecture and organization based on cache memory. So you can see the question is saying that consider cache memory with 32-bit addresses. We have a cache memory with 32-bit addresses. Remember, when we say 32-bit addresses, then basically we are talking about the physical address. Okay, so you can see this is basically physical address size, means main memory address size. Okay, so this is basically the physical memory address size, or I can say physical address size means main memory address size. Okay, so the question is saying that we have a cache memory with 32-bit addresses, and this cache memory has 768 blocks. So these are basically lines. Okay, because cache memory has these many blocks, it simply means that these are basically lines. Okay, because remember the question is saying that you have a cache memory with these many blocks. Okay, so it means that in the cache memory we have these many lines. A block size, line size, that is basically 128 bytes. Tag are 17 bits. Okay, this is the tag size. How many sets are there, and what is the associativity of the cache? This is a very simple question. So we have a set associative cache. You can see, actually whatever cache memory you take, direct mapped, fully associative, set associative, all these different type of cache memories, they are basically set associative cache. Okay, very simple. Remember, if you have direct mapped cache, then in the direct mapped cache you can assume that it is a set associative cache where every set has one line. Okay, means associativity is equal to 1. And remember, fully associative cache, it means the entire cache memory is a set. Okay, so if you have, let's assume n number of lines, total n number of lines, then fully associative cache can be considered as a set associative cache with associativity n. Means basically the entire cache memory, all the lines, these are in a single set. Okay, so remember, whatever type of cache memory you have, you can always consider it, you can always consider any type of cache memory as a set associative cache memory. Okay, so basically you have a set associative cache memory and we don't know the associativity. So let's assume that associativity is n way. Okay, so let's assume we have n way set associative cache. And the question is saying that the tag size, that is 17 bits. You can see. And also the number of lines, 768 in the cache memory, the number of lines, that is 768. Next you can see the block size, that is 128 bytes. Okay, next you can see that the physical memory address size, that is 32 bit. Okay, so in the set associative cache memory, the physical address we can divide into three parts, and the three parts are basically block offset. So this is basically block offset, or you can call it offset, or you can call it byte offset. And you can see this middle part, this is basically index, or I can say set index. In the set associative cache memory, it is set index. In the direct mapped cache, it is line index. And you can see here you have tag. Okay, and total this is basically 32 bits. Okay, you can see 32 bit address, so 32 bits. And finally you can see here tag is 17 bits. And what is the block offset size, means how many bits are required for block offset. So you can see that this block size is 128 byte. It means in a single block you have total 128 byte. So if I want to identify one of the byte, then how many bits I need? That will be 7 bits. Yes or no? So you can see that block offset needs 7 bits. Okay, so here you need 7 bits, here you need. And tell me, for set index, how many bits will be remaining? So that will be 32 minus 17 minus 7, these many bits. Okay, so you can see for set index, how many bits we need? How many bits are there for set index? So that is basically 17, 32. You can see 17 and 7, that is 24. So 32 minus 24, that is basically 8 bits. Okay, and finally I can say that if set index bits, if that is 8 bits, remember this will indicate the set number. Okay, the set index, it will indicate which set. Okay, so you can see if you have 8 bits in the set index, then total, what is the number of sets? The total number of set, that is 2 power 8. Yes or no? This is the number of set. So total number of set we have 2 power 8. You can see number of set, that is 2 power 8. And what this question is asking? The question is asking that, okay, number of set, the question is asking, so the number of set we found, that is 2 power 8, means 256. Okay, and what is the associativity? So you can see if you have n way set associative cache, means every set has total n lines. Okay, so total we have 2 power 8, or I can say 256, these many set we have. And total number of lines, that is 768. So tell me, in one set how many lines you have? Number of lines per set, that is your associativity. Yes or no? So you can see that what is associativity? Associativity of cache, that is number of lines per set. Okay, so you can see that how many lines will be there per set? Total we have 768 lines. Okay, you can see total we have these many lines. And total we have how many set? 256 set. 256 set. So finally what we got? We got number of lines per set. Yes or no? Okay, what we got? We got number of lines per set. So you can calculate this. I think this will be 3 lines per set. This is the associativity. Okay, very simple. So the answer will be 3-way set associative, 256 set. The answer will be option B. Now, many of you might be thinking how we can have 3-way set associative, because the associativity, it should be power of 2. Yes or no? So let me tell you, practically the associativity is always power of 2, but theoretically the associativity can be any number. Okay, the associativity can be 1, 2, 3, 4, 5, 6, any number. Okay, so remember, theoretically, basically this 3-way set associative, this is theoretically possible. Okay, theoretically valid. But of course, practically we want everything in the power of 2 inside your computer system. Whatever you have, basically we want that in a power of 2. Okay, for example, the number of lines, the number of blocks. Okay, so the associativity, all these things, if they are in power of 2, then things become very very easy. Okay, the calculation becomes very easy. Okay, the hardware, all these things become very easy. So you can see that here, this three-way set associativity, this three-way associativity, or I can say associativity equal to 3. Remember, this is theoretically valid. Okay, so for this question the answer will be option B. I think this was a easy question. What do you think? Anyone made silly mistake in this question? Anyone made any mistake in this question? Let me know. Okay, so let's move on. Let's solve this question from computer organization and architecture based on pipeline concept. So the question is saying, suppose we have 8 stage pipeline that can complete one instruction each clock cycle in the absence of any jump or branch instructions. Means, if we do not have any jump or branch instructions, then our 8 stage pipeline can complete one instruction each clock cycle. You can see we assume that there are no data or structural hazard in our pipeline. We do not have any data hazards, we do not have any pipeline hazards. Very simple. For jump or branches, the destination of the jump is known at the end of the pipeline second stage. So remember, at the end of pipeline second stage, the destination of the jump is known. And you can see, whereas the decision of whether a branch is taken is determined at the end of pipeline's fourth stage. At the end of pipeline's fourth stage, we will get to know whether the conditional branch instruction will be taken or not. Okay, conditional branch will be taken or not. Remember, jump means unconditional branch. You can see it is written here. Jump instruction means unconditional branch. So jump instruction will always be taken. Okay, as soon as you find out that it is a jump instruction, it will always be taken because it is unconditional branch. And you can see branch instruction. Branch instruction means conditional branch instruction. So they can either be taken or they can be non taken, I can say not taken. Okay, so you can see that the decision of whether a branch is taken is determined at the end of pipeline's fourth stage. Assume that 5% of instructions in a typical program are jump instructions, means unconditional branch instructions. So they will always be taken. You can see, while 15% of instructions are branch instruction, means conditional branch instructions, of which 2 by 3 are taken. You can see, let m be the average number of clock cycle per instruction if we speculatively basically predict. Okay, so remember here, this word actually it means predict. Okay, prediction, we are basically doing predict. So you can see we are doing a prediction here. So you can see that let m be the average number of clock cycles per instruction if we speculatively execute assuming that branches are not taken. Means this is our prediction that branches are not taken. This is called predict not taken. Okay, the another name for this, the another standard name for this, that is predict not taken. And you can see this strategy where we are assuming that branches are taken, this strategy is called predict taken. Okay, so you can see that this n is the average number of clock cycles per instruction if we speculatively execute assuming that branches are taken. Okay, so branches are taken. So this actually basically what it means here, it actually means predict taken, predict taken strategy. Okay, very simple. Now the question is asking what are m comma n respectively. Actually this is an easy question, and this type of many questions we have done in go classes pipeline lectures, also in the previous mock test, in our subject wise test, topic wise test. This type of question you may have seen. Okay, so let's solve this question. It is not a hard question. Let's solve this question. So first let me write the data that we have, that is given to us. So you can see that we have 8 stage pipeline. We have 8 stage pipeline, and the question is saying that in the at the end of second stage we will get to know we will get to know the destination of the jump instruction. Okay, so remember, at the end at the end of second stage at the end of second stage, what we will get to know? We will get to know the dest- the basically the branch address, yes or no, or I can say the destination of jump. So you can see the destination of jump. And you can see at the end of fourth stage, what we will get to know? At the end of fourth stage, we will get to know whether branch will be taken or not. Okay, yes or no. So basically, decision of branch taken or not. Okay, now let's solve this question. First we will solve this question for the strategy, that is predict not taken. Okay, so you can see, if you are using this strategy predict not taken, then what will happen? Then what will be the average execution time per instruction? So you can see the question is asking the average number of clock cycles per instruction. So already the question is saying that if you do not have any jump or branch instruction, then ideally you can see that the pipeline, what it will do, in this pipeline you can complete one instruction per clock cycle. Okay, so you can see for the normal instructions which are not jump instruction, which are not branch instructions, basically it will take one clock cycle per instruction, yes or no. But now you can see for the jump instruction or for the branches instruction, what will happen? Remember, jump means unconditional branch and branch means conditional branch. Okay, so you can see here, when you implement this strategy predict not taken, then you can notice that let's make categories for the instructions. Okay, so you can see that, if you can see the instructions can be of three types. Okay, so you can see normal instruction, which is not a jump instruction, which is not a branch instruction. Okay, so let's call it normal instruction. So the normal instruction, it will take one cycle. Okay, yes or no. So the normal instructions, they will execute one instruction per clock cycle. Okay, so you can see one instruction each clock cycle it will execute. So let's see the next. You can see the instruction can be jump instruction. If the instruction is jump instruction, then tell me how much time the jump instruction will take. You can see that this jump instruction, remember jump instruction means we will definitely jump to the target address, to the destination address, yes or no. Okay, so here remember, for the unconditional jump instruction, we don't have to wait for the decision whether the branch will be taken or not, yes or no. The jump instruction, it is unconditional branch instruction, so it will always execute the instruction at the destination address, or I can say basically the branch address, or I can say the target branch will always be taken. There is no confusion here, yes or no. So but there is one thing here, that because of this jump instruction, what will happen? Let me tell you. Because of this jump instruction, you can see when the jump instruction enters the pipeline, let's assume this is a stage 1 and this is stage 2, stage 3, okay, and so on. You have stage 8. Now you can see when this jump instruction enters the pipeline and when this jump instruction is here, now you can see at the end of this stage, at this moment you will find out what is the target address, yes or no. At this moment, you will find out the destination of jump, or I can say the jump target address of jump, yes or no. Okay, and one more thing, remember, it is guaranteed that I will go to this address, yes or no. So remember, there are two ways. What are the two ways? Either we will not fetch the instruction. See, as soon as the jump instruction we fetch, then we stop fetching the next instruction. That is one way. Let me tell you, in the first stage, if you are decoding, see, there are two possibilities. In the first stage, if you are decoding, means in this first stage you are finding out that the instruction is jump instruction. Then in that case, what we will do? Then when the jump instruction will go to this stage 2 in S2, then what we will do, we will not fetch the next sequential instruction. Okay, are you getting my point? But remember, if in this stage 2, if you are finding out whether this instruction is jump instruction or not, means basically this stage 2 is your decode stage. In that case, remember, there is sequential instruction already here. So I am telling you that there are two possibilities. There is possibility 1. There is possibility 1. Possibility 1. What are the possibility 1? Please understand. The possibility 1 is that this stage is your decode stage. Okay, let's assume here you are doing decoding. Here you are decoding also. Okay, fetching and decoding. Let's assume decoding and fetching, fetching and decoding. So in this stage, let's assume you are fetching instruction also from the instruction memory and you are decoding also. Okay, in this situation, you can see when the jump instruction will go to stage 2, then here there will be no instruction. Okay, none here. So you can see in this possibility 1, you can notice we are getting one stall, we are getting, yes or no? This stall we are getting, basically one cycle is wasted. Okay, so overall I can say that this jump instruction is basically taking 2 cycles, because please understand that at the end of this S2, you will get to know the target of the jump, and because this jump is unconditional branch instruction, so we will definitely go to the target of the jump instruction. So I can say that here from at this moment I will definitely fetch this target address. Okay, yes or no? This instruction at the target address, this I will definitely fetch here. So I can say that in this possibility 1, overall I can say that this jump instruction is basically consuming 2 cycles. Okay, yes or no? For every jump instruction it is consuming 2 cycle, because you can see one cycle is actually wasted. Okay, there is none here, so you can see one cycle wasted. So overall I can say in this possibility, you can see that jump instruction is basically overall it is taking overall consuming 2 cycles. Overall it is consuming 2 cycles, or I can say that it is basically consuming 1 cycle, but there is one stall also, 1 cycle wasted. So overall it is consuming 2 cycles. This is the possibility 1. What is the possibility 2? Tell me, what is the possibility 2? Let me write that also. So you can see possibility 2. Possibility 2, that is basically that in this stage you are decoding. In this stage you are decoding. Now in this situation, you can see there is a sequential instruction in this stage S1. Yes or no? Okay, so you can see in this S1 we have the next instruction, I next. I next means in the fall through path, or I can say in the text, in your program text, the after jump instruction, which instruction you have. Okay, so you can see, let's assume there is an instruction I already here, because remember in this S2 you will get to know that your instruction is jump instruction. So by that time already in this stage S1 we have already fetched the next instruction in the fall through path, means the next instruction after the jump instruction in the program text. Okay, is this clear? So in this situation you can see in this S2 we will find out whether this instruction is jump instruction or not. And then because this jump instruction will definitely be taken, means I can say because of this jump instruction, the next instruction that I need to execute, that is basically the instruction at the target address. So definitely what I need to do, this instruction this is a wrong instruction in the pipeline, so I need to flush it. Yes or no? I need to flush it, means I need to clear it. Okay, so we will flush this instruction I. Is this clear? Let me know. So again you can see that because you are flushing this instruction I, again one cycle got wasted. Okay, so again overall you can see that this jump instruction overall again it is consuming 2 cycles. Overall consuming 2 cycles. Okay, so this is just for sake of complete analysis I am telling you, so that you don't have any confusion. But remember, whether you take possibility 1, whether you take possibility 2, whatever possibility you take, the final conclusion, what is that? The final conclusion is that this jump instruction is basically consuming overall 2 cycles. Okay, yes or no? Including one, in this 2 cycle already we have included the one stall. Okay, yes or no? In this 2 cycle already includes including the stall, including one stall cycle. Okay, is this clear? Very simple. I hope you understood this. So this is the complete analysis of the jump instruction. Now what is another type of instruction that we have? That is your conditional branch instruction. Okay, in this conditional branch instruction also you can see there are two possibilities. Either it will be taken or it will not be taken. Yes or no? Actually taken. Actually taken means actually it will be taken. And another possibility is that actually it will not be taken. Yes or no? And now you tell me, if it is actually taken, if this branch is actually taken, but what you are predicting, first let me discuss actually not taken. Okay, this is easier. So first let's discuss actually not taken. You can see, if your branch is actually not taken, what it means? It means that the correct next instruction to execute, that is basically the next instruction in the fall through path. Yes or no? Or I can say in the program text, the next instruction of this branch instruction, that is the correct next instruction to execute. Okay, do you agree with me? Okay, because already I am saying that this branch is actually not taken, means the condition will become false and you will not go to the instruction at the target address. You will not go there. So you will execute the next instruction in the fall through path. You will execute the next instruction after next instruction immediately after this branch instruction in the program text, or I can say in the fall through path, the next instruction you will execute. And you can see that we are already predicting that the branch will not be taken. Okay, so it means that in this situation there will be no stall. Do you agree with me? In this situation there will be no stall, or I can say that it will take overall, it will consume one cycle only. No stall. No stall. Did you understand what I'm saying? See, let me just explain. This is an important question, and many students have confusion in this type of question. That is the reason I'm explaining this point. Let me explain. You can see our prediction. What is that? Our prediction is not taken. This is our prediction not taken. Okay. So this is prediction for conditional branches. Remember, for conditional branches, this prediction we make. Okay, so here let's assume this is your program text and you have a branch instruction, conditional branch instruction. Let's assume that you have a branch instruction I. Okay, or let me call it I5. Now you can see this is I6, this is I7, this is called fall through path. Okay, and let's assume that the target, okay, this branch instruction I5, it has some condition like this. Let if A is less than B, okay, some condition. You can see if A is less than B, then jump where? Go to let's assume I100. Okay, so you can see this I100, this I100 is here. Okay, is this clear? So basically this address is called the branch target address. Okay, is this clear? This is called the branch target address. Branch target address. At this branch target address, you have this instruction I100. Okay, is this clear? Very simple. So now you can notice that when you fetch this instruction I5 in your pipeline, okay, in this is your pipeline, and this is the stage S1, this is the stage S2, stage S3, stage S4. We only care about these stages, and there are some more stages S8. Okay, so you can see total we have 8 stage pipeline. Now you can notice one thing, that when this instruction I5 I will fetch, then instruction I5 will go through these stages. And remember, either in this stage or in this stage, we will get to know that our instruction is basically branch instruction. Okay. Now let me tell you, you don't have to worry in which stage we are decoding. You don't have to worry about it, because that information is not given in the question. So you can solve in a generic way. This suggestion I am giving to all of you, that in the question it is not given when we are decoding. Means in the question it is not given that in which stage we will find out that our fetched instruction is a branch instruction. Okay, yes or no? In some stage we will find out that the instruction we are fetching is actually a branch instruction. Yes or no? So because this information is not given, that in which stage we will find out that our fetched instruction, the instruction that we are fetching, is a branch instruction or not. So basically, in which stage we are doing the decoding, this information is not given. So in this type of situation, I strongly recommend you that you just assume that in the first stage itself we are already knowing that the instruction that we are fetching is a branch instruction or a jump instruction or a normal instruction. Okay, is this clear? So remember, in this type of generic question, in this type of generic situation, you can assume that in this stage we are decoding. Okay, let's assume. Is this clear? In this stage we are fetching and decoding. This simple assumption you can make. This simple assumption you can make in this type of generic question. Okay, is this clear? This is a valid assumption to make. Remember, in this type of questions, this is a valid assumption to make in this type of question, because in the question it is not given that which stage is your decode stage. So in this type of generic question, which are basically focusing on the predict taken, predict non taken, these branch, I can say, branch resolution strategies. Okay, so you can see in this type of questions, this is a valid assumption to make that in the stage 1 itself we are fetching and decoding. In the stage 1 itself we are finding out whether the instruction that we are fetching is a branch instruction, jump instruction, or is it a normal instruction. Okay, so very simple point. Now notice that this instruction, when you are fetching this in the stage 1, we will find out that this instruction I5 is a branch instruction. Okay, so tell me, when this instruction I5 will go here, then what we will do here? Let me know, because remember, at this moment you will find out, at the end of the stage 4, at this moment you will find out whether we should execute this I100 instruction or we should execute this I6 instruction. Yes or no? At this moment the branch is resolved. At this moment the branch is resolved. Okay, is this point clear? At this moment the branch is resolved. I hope you understood this point. So remember, when this instruction I5 is in the stage S2, then tell me what will be there in the stage S1. Very simple question I am asking. You can notice, when this instruction I5 was in the stage S1, then we are already decoding this instruction and we are finding that this instruction is actually a branch instruction. Now for the branch instruction, we are using this prediction that it will not be taken. This is our prediction. So when this branch instruction I5 will go to the stage S2, then because it is our prediction that it will not be taken, remember, in the stage S4, at the end of the stage S4, we will find out whether it will actually be taken or not. But already at this point, when you are in the stage 2, then at this point it is our prediction that the branch will not be taken. So because of our prediction, what we will do? We will fetch this instruction I6, because we are already making a prediction. We are making this prediction that because this instruction I5 is a branch instruction and our prediction is that the branch will not be taken, so it is a common sense that we will fetch these instructions. Yes or no? Yes or no? So this is called fall through path. This is called fall through. This is called fall through path. So here I will fetch the instruction I6. Now notice, when this instruction I5 will go to the next stage, when this instruction I5 will go here. Now at this moment also we do not know whether the branch will actually be taken or not. Means at this moment also we do not know whether the next instruction to execute will be from the taken path or from the fall through path. We don't know. So our prediction is that the branch will not be taken. So it is a common sense that we are assuming that these instructions should be executed next. Yes or no? So you can see, when I5 is here, then I6 will be here and I7 will be here. Yes or no? Now when I5 will be in the next stage, means when the I5 is here, then already I6 is here, I7 is here, I8 is here. Okay, but notice, at this moment you will get to know whether the branch is actually taken or not. Means the branch is resolved at the end of the stage S4. So now you tell me, if your prediction is correct, then what is the cost you have to pay? And if your prediction is not correct, then what is the cost you have to pay? Tell me one thing. Let's see the cost. Let's see the cost of prediction. let's say the cost of prediction. We are making this prediction, so let's see the cost of prediction. You can see, if your prediction, there are two possibility. If your prediction is correct, either your prediction will be correct or your prediction will be wrong. So you can see, if your prediction is correct, then tell me how many cycles will be wasted. Let me know. If your prediction is correct, then how many cycles will be wasted? Then no cycle will be wasted. If your prediction is correct, then it means, if our prediction is correct, then it means that branch is not taken. Means actually we should execute these instructions, I6, I7, I8. These instructions actually we should execute, and we are already executing them in the cycle, in the pipeline. Okay, inside the pipeline already these instructions are executing. So here basically there is no stall. Okay, there is no stall here. And if our prediction is wrong, then what are the stall, what are the number of stalls? You can see, at the end of the stage S4, we will find out that actually the branch will be taken. Means after this I5, the next correct instruction to execute, that is actually I100. So these instructions I6, I7, I8, they should not be executed after I5. Yes or no? So definitely these instructions I7, I6, I7, I8, these instructions I must flush. Yes or no? So these three instructions I should flush. So that means basically three stalls, three cycles wasted, I can say. Okay, because I have to flush I6, I7, I8. So three cycles got wasted, or I can say three stalls, or I can say three cycles got wasted. Is this clear? So this is the complete analysis. I hope you understood this. Very simple. Okay, so very simple. Now here I can say that if actually taken, then total how many cycles? If the branch is actually taken, then total 4 cycles. Total overall 4 cycles. You can say that this branch instruction, for which actually the branch will be taken. Okay, for this type of branch instruction, for which actually the branch will be taken, overall I can say it is basically consuming total 4 cycles, in which 3 cycles are basically stall cycles. So total 4 cycles. In this includes, it includes 3 stalls, 3 wasted cycles, includes 3 wasted cycles. Okay, that's it. I hope you understood. Now this question you can, I think you can very easily solve. So for the predict not taken, what will be the final answer? Tell me. You can see, already we have that how many instructions are normal instructions. The question is saying the number of normal instructions. You can see the question is saying that 5% instructions are jump instruction and 15% are branch instructions. So basically 80% instructions are actually normal instructions. Okay, so you can see that 80% instructions, normal instructions 80%. I can say normal instructions, these are 80%. These are 80%. Okay, and you can see jump instructions, these are 5%. Okay, and you can see the branch instructions, these are 15%. And now you can see in this branch also, you can see that out of this also 2 by 3 are actually taken. 2 by 3 actually taken. Okay, so what that means? 2 by 3 actually taken means 10%. Yes or no? I can say that 2 by 3 actually taken, that simply means that 10% are actually taken. 10%. And you can see that 1 by 3 not taken. Actually not taken. Yes or no? Actually not taken. So that is basically again 5% are actually not taken. Okay, and now you can easily solve this question. For a normal instruction, it takes 1 cycle. Okay, 1 cycle. And you can see for jump instruction, we have already seen 2 cycles overall, including 1 wasted cycle. Okay, it includes 1 wasted cycle. And here you can see that they will take, which are actually taken, they will take 4 cycles. including three wasted cycles. Okay, and which are actually not taken, they will take one cycle. Now you can solve this question very easily, right? So finally, what will be the answer? The answer will be that 80% instructions, that means 0.8. Okay, so you can see the number of cycles per instruction, the CPI. Okay, the CPI, what that will be? That will be for 80% instructions, it will take one cycle, plus for jump instructions, that is 0.05 instructions. Okay, for them, two cycles, plus you can see that the branch instructions which are actually taken, so those are 10%. Yes or no? 0.1, 10% means 0.1. These will take four cycles, plus the 0.05. These are the branch instructions that will actually be not taken. Okay, so they will take one cycle. So you can calculate this value. That will be your CPI. I hope you understood this. Okay, let me know. Is this question clear? See, I'm explaining this question in a very detailed way because I am very sure that this type of question you will find in the future gate exam, because I've gone through many standard resources, and in most of the standard resources in the pipeline you will find this type of question based on predict taken, predict not taken. These type of questions have already come in the gate exam in the past. Also, these are very strong candidate for coming in the future also. That is the reason I am explaining this question in a very detailed way. I hope you understood the everything. I hope you understood in a crystal clear way. Let me know. Please tell me, can you say that in a very crystal clear way you understood this complete explanation? Like this predict not taken, this strategy, did you understand in a very crystal clear way? Let me know. Now we will understand the predict taken strategy. Okay, so let's understand now the predict taken strategy. Once you understand these strategies in a crystal clear way, then very easily you can solve all these questions. These are actually not hard questions. Okay, so let's focus on the predict taken strategy. Now in this predict taken strategy, what happens for the jump instruction, what happens for the branch instruction? Let's see that. Okay, so you can see first our prediction. You can see our prediction for branch instructions. For conditional branch instructions, remember. Okay, for unconditional, for unconditional branch instruction, there is no such thing as prediction. Yes or no? Because unconditional branches, they will always be taken. Unconditional branches, they will always execute the next instruction at the target address, not the next instruction in the fall through path. Yes or no? So you can see basically prediction for conditional branches, conditional branch instructions. Okay, so what is our prediction? Our prediction is that it will be taken. Okay, you can see means branch taken. Now let's understand what happens for the jump instruction. For the jump instruction, what will happen? Jump instruction means, this means unconditional branch. So for jump instruction, what happens? Let's see that. You can see the jump instruction, it will always be taken. Okay, because it is unconditional. So you can see, let's assume that this instruction I5, let's assume this is a jump instruction. Okay, this is a jump instruction, jump at I100. Then you can see this is I6, this is I7, and so on and so on. Here you have I100. Okay, very simple. Now notice that when you face this instruction in your pipeline, this is your pipeline, and in this pipeline, this is the stage S1, stage S2, stage S3, and so on. So here, when the jump instruction we fetch, then let's assume that in this first stage itself, you are fetching and decoding. Okay, and remember, this is a valid assumption for this question. For this type of generic question where it is not given in which stage we are decoding. Okay, so in this type of question, it is a valid assumption that you can assume that in the first stage itself you are fetching and decoding. You are fetching and decoding means in the first stage itself we are finding out that our instruction that we are fetching, this instruction is actually a jump instruction. Okay, is this clear? So very simple, this is a valid assumption for this type of generic question. Okay, so here you can see this instruction I100, sorry, this instruction I5 we are fetching, and when this instruction I5 will go to S2, when this instruction I5 I2 is here, sorry, I5, when this instruction I5 is here. Okay, now you already know that the question is saying that at the end of stage 2 we will find the target of the jump instruction. Okay, yes or no? Here we will find the destination, or I can say the target of jump. The target of jump instruction we will find here. Okay, at the end of stage S2 we will find out the target of the jump instruction. Very simple. Now you notice one thing, that because in this stage S1 we are already fetching and decoding, and we found out that this instruction I5 is a jump instruction, so definitely this target instruction, this will be executed, yes or no? So you can see this target of the jump instruction, this instruction will basically execute next. So definitely we will not fetch the next instruction, yes or no? Okay, so this is a stall. So one cycle got wasted, yes or no? When this stage I5, when this instruction I5 is in the stage S2, then in this stage S1 we will not fetch the next instruction, this I6 we will not fetch, because there is no benefit in fetching I6, because it is 100% sure that next valid instruction to execute, that is basically I100. Okay, yes or no? So there is one stall cycle. So overall I can say that overall this jump instruction, because of jump instruction, overall two cycles got consumed, consuming two cycles, consumed two cycles. Okay, including including one stall, including one wasted cycle. Okay, one cycle got wasted, very simple. Now you tell me what will happen for the branch. For the branch instruction, what will happen? Now if you have a branch instruction, means conditional branch instruction you have. Again, let me assume that this I5, this is a conditional branch instruction. Okay, so this is some branch instruction, something like this. Okay, if a greater than b, if a is less than b, then go to I100. Okay, this type of instruction. Now you can see this is I6, this is I7, this is I8, and here you have I100. Okay, so very simple. Now this is the target of the branch. This is the target of the branch instruction I5. Okay, now let's assume that you are fetching this instruction I5 in your pipeline. Okay, so you have stage S1, stage S2, stage S3, stage S4. Okay, there are more stages. So you can see that you are fetching this, instruction I5. Now tell me, when this instruction I5 is in the stage S1, then we are decoding, we are fetching and decoding, yes or no? So in this we are fetching and decoding. Now we found out that our instruction is actually a branch instruction. Okay, conditional branch instruction. Now whether the branch will be taken or not, means the next valid instruction to execute, whether that is I6 or I100, that decision will be made here. Okay, so here the branch is resolved. At the end of stage 4, the branch is resolved. Okay, so now you tell me, when this instruction I5 is in stage S2, I5 is here, then tell me what you will do in S1. Let me know what you will do in S1. Will you stop fetching? Very simple question I'm asking. when this instruction I5 is in the stage S2, then will you stop fetching I6, I7, I8? Will you stop fetching? Yes, we will stop fetching. Yes or no? Why we will stop fetching? Because we are already making this prediction that branch actually will be taken. Yes or no? This is our prediction that branch actually will be taken. Yes or no? Okay. So please understand that when this when this instruction I5 is in the stage S2, then we will not fetch I6, I7, I8. These fall through. This is the fall through path. Please understand, when this instruction I5 will be in the stage S2, it is a common sense, because our our prediction for conditional branches, that is that branch actually will be taken, means already we are assuming in our mind we are already assuming that after this I5, the next instruction to execute, the valid next instruction to execute, that is basically I100. Okay, yes or no? In our mind we are already assuming that after I5, this I6 should not be executed, this I100 should be executed. Yes or no? So you can see that here I will not fetch anything. Okay, is this clear? Here I will not fetch none. But notice one thing. At the end of S2, now at this moment I will find the target address. The target address I will find here. The question is saying that target address will be available at the end of stage S2. But remember, we have the target address with us, but we don't know whether the branch will actually be taken or not. Remember, the branch will be resolved at the end of stage S4. But at the end of stage 2, this target address is available to us. Now, think, just use your common sense, think logically. I am thinking this is my prediction that branch will actually be taken. Means I am very sure, I am 100% sure that after I5, the next instruction to execute, that is actually I100. Okay, yes or no? So what I will do, as soon as I will find the target address, this I100 address, as soon as it is available to me at the end of this stage S2, so next I will fetch this I100. Do you agree with me? Yes or no? So notice one thing, that what I will do like this, that when this instruction I5 is here, now remember, here I will fetch none. Here none I will fetch. And here I will fetch I100. This is interesting. Do you agree with me? This is just a simple common sense. Do you agree with me? Let me know. Did you understand this point? It is a very simple point, because for conditional branches, it is our prediction. In our mind, we have made a pre-assumption. Our pre-assumption is that this after this I5 instruction, the next correct instruction to execute, that is actually I100. So definitely I will not fetch I6, I7, I8. I will never fetch them. Okay, because this is my pre-assumption that the branch will be taken. This is my prediction that branch will be taken. So I will not fetch I6, I7, I8. Okay, now notice one thing, that at this moment the branch target is available to me. I don't know whether actually the branch will be taken or not, but actually the target address is available to me here. The target address, I100 is available to me here. Okay, so what I will do, because of my pre-assumption, because of my prediction, I am thinking that after this instruction I100 should be executed. So what I will do, at the end of this stage S2, I will find this target address I100. So what I will do, I will fetch it. Yes or no? I will fetch it. Very simple. Now notice, when this I5, will go here, okay, at this moment there is none here, there is a stall here, okay, and then here I100, and then here I101. Okay, so like that. Is this clear? Very simple. Now again you notice, at the end of this stage S4, we will find out whether the branch will actually be taken or not. Okay, yes or no? So if my prediction is correct, then what will be the cost? And if my prediction is not correct, then what will be the cost? Now you just tell me the cost of my prediction. From here, you tell me the cost of prediction. Our prediction was branch not taken. Predict. Our prediction was branch taken. Sorry, our prediction was branch taken. This was our prediction, branch taken. Okay, now you tell me the cost of prediction. Cost of our prediction. So you can see, if my prediction is correct, then how many cycles will be wasted if the prediction is correct? And if the prediction is wrong, then how many cycles will be wasted? Simple question I'm asking. If the prediction is correct, now you can see, prediction is correct means actually the branch will be taken, and that is my prediction also. So if my prediction is correct, then after I5, I100 will execute. So you can see, if my prediction is correct, then also one cycle got wasted. Yes or no? Why this one cycle got wasted? Can anyone tell me? This one cycle got wasted because when when I'm in this stage S1, I don't know, the target. Yes or no? The target address I don't know. Is this clear? At the end of stage S2, I will find the target address I100, so I can fetch it. But when I'm in the when the this branch instruction, when it is in the stage S1, then we do not know the target address, so definitely we cannot fetch this I100 here. Yes or no? But remember, after the stage S2, we will find this target address, and because of our prediction, because of our pre-assumption, we will fetch I100. So you can see that even if our prediction is correct, then also one cycle got wasted. Yes or no? If our prediction is correct, then also one cycle wasted. One cycle still got wasted. Okay, yes or no? I can say one stall. And you can see, if our prediction is wrong, then what will happen? Now something interesting will happen. If our prediction is wrong, it means these I100, I100 and I101, these instructions that you have fetched, these instructions are wrong instruction and you have to flush them. So three cycles got wasted. Already one cycle and two cycle these. So total three cycles got wasted. Three cycles wasted. Yes or no? Okay, and here what we will have to do? We will have to flush I100, I101. These I have to flush from the pipeline. Okay, yes or no? I hope you understood. So that's it. This is the overall conclusion. Now we can easily solve this question. So you can see, now we can easily solve this question. So for this predict taken, basically we just have to find that if you have a normal instruction, and how many instructions are normal instructions? You already know that 80% instructions are actually normal instructions. Okay, and if you have a jump instruction which is a unconditional branch, how many? 5% are jump instruction. And if you have a branch instruction, okay, then remember 15% are the branch instruction. Okay, and here also either the branch will be taken or the branch will not be taken. Okay, the branch will actually be taken or the branch actually will not be taken. Actually taken, actually not taken. Yes or no? So here basically we just have to find that how many cycles here, what is the number of cycles, what is the number of cycles. Okay, here also we have to find what is the number of cycles, and similarly here also number of cycles, and here also number of cycles. Okay, so now you can actually easily find, after our analysis we can easily write. Okay, already the explanation we have seen. So finally now what I can say, that for the normal instruction one cycle will be taken. It is given in the question that the instructions which are not jump instruction, the instructions which are not branch instruction, basically if an instruction is a normal instruction which is not jump not branch, then it will take one cycle. Okay, very simple. Per instruction, in one cycle one instruction will be executed. And you can see for the jump instruction we have already seen two cycles taken. Okay, including one wasted cycle. And you can see, if the branch is actually taken, then here also two cycles. Why two cycles? It includes one wasted cycle. Yes or no? And if the branch is actually not taken, then total 4 cycles, including 3 wasted cycles. Okay, is this clear? Let me know. Very simple point. Okay, so if you want, I can write it like 1 plus 1. Okay, so if you want, I can write it like this, that 1 plus 1. Here also I can write 1 plus 1, and here I can write 1 plus 3. Okay, these are the stall, or I can say wasted cycles. Okay, is this clear? Very simple. So finally, what will be the answer? So for predict taken, for predict taken strategy, what will be the CPI, average CPI? So the average CPI, that will be, you can see, for normal instruction, 80% are normal instructions, so 0.8, they will take only one cycle per instruction. And you can see, if you have jump instruction,